All right, so section 7.3, we are going to prove triangles similar. So we're not going to do proofs per se, but we're going to look at pictures and determine whether they are similar or not. So we need to talk about the different ways to prove triangles similar. They are not the same ways that we use to prove triangles congruent. Okay. So the first way is called angle-angle similarity. So what it says is, if you have two angles congruent to two angles, then the triangles are similar. So it's angle-angle similarity, just needing two angles. Well, let's go into Desmos geometry and let's take a look at this real fast. All right. So I'm going to start in Desmos geometry. Oh, give me 1 second. Sorry. Yep. Desmos geometry. So I'm going to start with a triangle. Okay. And I'm going to measure two angles, 58 and 78. So I'm going to make a triangle that I think looks similar to this triangle and try to have the angles of 58 and 78 involved. So let's go here. So you can see I just kind of did like a mini-me triangle, right? How good am I, right? 58 degrees. What if this is 78? How much money are you going to give me? Oh, 86. Dang it. So let me move this so it becomes 78. There. Okay, good. So first of all, we should know that the third angles are going to be congruent. And I didn't show this yet, but I'm going to present. So the reason that we don't need AAA, right? So we don't need angle, angle, angle because of this third angles theorem, which I taught you back in the congruent triangles chapter, where if you know that two angles are congruent, you know the third are. And again, that's the fact that the sum of a triangle is always 180. So if I know these two, I know angle C. If I know these two, I know F. Okay, so that's why it's just angle, angle. If you put angle, 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 I think Delta Math actually has angle, angle, angle. You're not wrong, but it's just not necessary according to this book. Okay, so coming back here, so are these two triangles really similar? Well, again, like I said, the third angles should be congruent, and they are. And now, what about the side lengths? So this side, what did I do that for? The side lengths. Label that side 3.06. Now let's label this side right here 1.38. Now I'm going to put that in a ratio in Desmos graphing calculator. I'll put the bigger side on top. 3.06 divided by 1 point, I think it was it 1.38. That's a ratio of like 2.2, okay? So let's do another pair of corresponding sides. Let's do this bottom side, 4.3, and that side, 1.95. So let's do 4.3 divided by 1.95. And look, pretty darn close, 2.2. Let's do the third pair of sides right here. What do we got? 3.71, 1.7. So let's do 3.71 divided by 1.7. And look at that, 2.18. These three ratios are roughly all the same. Again, we're limited to Desmos geometry. So I just created two similar triangles, and all I started with was the 58-degree angle and the 78-degree angle. So you should believe that angle, angle is enough to know that two triangles will be similar. Okay. All right, next idea. Let's make this bigger. So the next way is by side, angle, side. So now, if I know in two triangles that I have one pair of angles congruent, and then the surrounding sides are proportional, not congruent, not similar, but proportional. If I know this much, then I know that the triangles are similar. All right, so let's try to do our magic with this situation, with one angle and the two sides that surround it. Now I'm going to make the numbers hopefully a little bit better, easier to see, so I don't have to use a calculator, right? So here is, there's one triangle, and I want to make it look like that. There, okay. So let's see what this angle is here. 73, sure. And then let's measure this side. Oh, no, let's measure this side. And I'm going to make that 2.6, okay? And then let's measure this side. 4.25. Let's go ahead and make that 4. Can I do that? 4? Yes. So here is a side angle side case. So let's do the same thing with another triangle and see what happens, right? So we're going to make it a little bit smaller. And again, you think I can make a 72-degree angle? I'm not sure. I tried my darndest. Let's see, 72. 74. But now I have to play with the sides too. So let me measure the sides. So I'm going to go half. What is half of 2.6? Half of 2.6 is 1.3. So let me make that 1.3 if I can. There, 1.3. And now let's measure this bottom side here. Okay, well, what's half of 4? Half of 4 is 2. So there's my bottom side of 2. And then let me make this angle 72. Oh. So I'm going to leave it at 1.99. Sorry, that's close enough, right? So what I've done is I've created 2 triangles where they both have a 72-degree angle, and then the sides surrounding them have a ratio of 1/2 or a ratio of 2, right? So half of 2.6 is 1.3, half of 4 is 2, which is really close to 1.99. So now let's measure the other angles. 70. Guess what this angle up here is going to be? 70. Let's measure this angle right here. 38. Guess what this angle is going to be? 38. Amazing. And now, that side is 4.06. What's half of 4.06? Around 2.03. Drum roll, please. 2.01. Boom. So these 2 triangles are similar, and all I knew was side, angle, side. All right, last but not least is your side, side, side case. So now I don't need any angle measure information. I just need to know that the 3 sides are proportional. That means they all have the same ratio. If I know that, then the triangles will be similar. Then the angles will be congruent. If my sides are proportional, then my angles will be congruent. Let's show this real fast. Okay, so again, let's try to use some nice numbers if I can. So here's my triangle. I can guarantee 2 nice sides, right? So let's make that 4. Okay. And let's make this 8.2 is good, right? I can take half of 8.2. So then what's this side going to be? 7.11, sorry. Okay. So now I'm going to make a triangle just like this, but half the size. So I want this one to be half of 4, which is 2. Oh, not even close. Close, but not even close. Okay, 1.99. Half of 8.2, which is 4.1. There. And then half of 7.11, which should be about 3.5, right? Let's see. So I got 3.24. So 7.11, if I take half of 7.11, 3.55. So I need to make this a little bit longer. So watch what I have to do. This takes a little effort, right? I need to make this longer without changing the 4.11. So watch what I do. I swing it down. So 3.55, but this has to be around 4.11. Oh, so close. Okay, close enough, right? So, no, not. Okay, that's all close enough, right? So we have about 4.1, about 3.5. So now let's look at these angle measures, right? So they might be a little bit off, like 1 degree, but who's the margins, right? It's all technology based. So here we go. Let's measure this angle in this corner. 1, 2, 3. 60 degrees. Guess what this angle down here is going to be? 60 degrees. Uh-oh. Top angle. 91. Guess what that's going to be? 91. Last angle here should be about 29. Guess what that angle is going to be? 29. So by taking 2 triangles and making sure that their sides were all half of each other or in a ratio of 1 to 2 or 2 to 1, I was able to get a triangle that has the same 3 angle measures, but the sides are just proportional. That is what similarity is. Pretty cool, huh? All right, so last but not least, so aside from proving or verifying that triangles are similar, you're going to do two other types of indirect problems. These problems are the shadow problem and then the mirror on the ground problem. So typically what happens is, they're going to give you, and I'm going to use capital letters and lowercase letters. They're going to give you a height for some object and a height for a person. They're going to give you the shadow of some object and the shadow of the person. Now, these triangles are going to be similar because they both involve this angle, and then we assume that objects are perpendicular. So this big triangle and this small triangle are going to be similar by angle-angle similarity. Therefore, our proportion can be the height of the tree over the height of the person should equal the shadow of the tree over the shadow of the person. Something like that, where you're putting corresponding lengths in the same ratios. This is the proportion we'll use to solve this problem. Same thing down here with the mirror on the ground. So when you have a mirror on the ground, you're going to have a height and a height. And then you have a length away from the mirror and a length away from the mirror, lowercase l, sorry. Now, in science class, you should have learned these things called angle of incidence and angle of reflection, right? So this angle that I'm looking down at this mirror is going to be the same as the angle bouncing off the mirror. That's a science idea. And then the same thing with the person in the Eiffel Tower. They are assumed perpendicular. So these two triangles, again, are similar by angle-angle similarity. So you're going to have the height of the object over the height of the person equals the length the object away from the mirror to the length that you are away from the mirror. And again, use that proportion to solve the mirror problem. All right, sorry for the lengthy video, but I got a couple example problems. There's several example problems to make sure you have a good idea of what similarity is all about.